This conference will now be recorded.
Hello, everybody. Thanks for joining us. Jordan Girth here from the National Weather Service Office of Observations. This is the Satellite Book Club Seminar Series, session number 7. We're going to be talking about ABI fire detection today with Chris Schmidt, who's a researcher and a long-time colleague of mine at the University of Wisconsin Space Science and Engineering Center. Just before we get started, wanted to remind everybody that this session is being recorded and will be posted online. So if you have a colleague that's unable to attend today, this will be available for them to listen to after the fact. If you have any questions, happy to take those. This presentation will be about 15 minutes. If you want to jot them down in the chat window, go ahead and do that. Anybody from the field in particular that's interested in presenting, we'd love to hear from meteorologists and how they're using satellite imagery and products to solve operational challenges. As always, we're looking to tailor this to meet your needs, so there is a survey that will be provided if you have any suggestions for improvements. And if you're looking for more information on training at your office specifically related to satellites, we have the Office of the Chief Learning Officer, Brian Mata, Russ Van Til. Please contact them. We've got a great team that can help you with building training. We just wanted to thank many people who are behind the scenes. We've got the Tower S team that does the AWIP support, Oklo, of course, GOES-R, and JPSS. So glad and thankful for those programs. Hope everybody's staying well. Today we've got Chris Schmidt, as I mentioned, from Cooperative Institute for Meteorological Satellite Studies at SSEC UW Madison. He started with Biomass burning team in 2002 and was tasked with making the WFABBA operational. He's been the algorithm lead for fires on the ABI, and he's working to update the fire detection algorithm and lining up resources for the next generation of fire algorithms. So, Chris, looking forward to your presentation. Thanks for being with us.
Thank you, Jordan. Yeah, we can go to the next slide. So I know we have a wide variety of levels of experience with fires from ABI and previous GOES online. So there will be some things in this presentation that may seem a bit elementary, others that may seem obtuse, and I welcome questions about that at the end. But I want to make sure that we cover some of the key bases as we go along. So ABI fire detection, it's a baseline algorithm, the fire detection and characterization algorithm. It was day 1, and it was basically a straight adaptation of the Wildfire automated biomass burning algorithm that was created for the previous generation of GOES. There weren't really resources put into taking true advantage of ABI's capabilities. Having said that, it doesn't do the worst job in the world. Its resolution is 2 kilometers. It's limited by the 4 micron band resolution, and it provides fire detections, fire rate of power, fire size, and fire temperature. It's contextual, so it does attempt to make accommodations for the scene it's looking at, but there are some fixed thresholds involved, and that does lead to some things that people experience with the algorithm. It currently runs on the 5-minute CONUS and 10-minute full disk sectors only. NOAA is not running the algorithm on 1-minute mesoscale data, which is a shame, as we'll cover a little bit later. Speaking of 1-minute mesoscale, that loop on the right happens to be 1-minute true color mesoscale with several fires in the scene, and the biggest one will come back later in the presentation. The algorithm requires the 3.9, 11.2 micron bands and optionally makes use of the red visible 0.64 and the 12.3 micron band. So it uses bands 6, 14, 15, and 2 in its current iteration. Go to the next slide, please. So I want to talk a little bit about what the characterization actually is. I know there are questions about this, and it's something important to understand. quantitative applications are what drove characterization in the first place, and fire size and fire temperature were the products that were first developed because those were the ones that modelers were asking for. The concept of fire radiative power came later. We get those size and temperatures by solving a pair of simultaneous equations that are up on the right. And we're basically taking the 4 and 11 micron data and a few other pieces of information and solving for the fraction of the pixel that's on fire and its temperature. While this is handy for coming up with fire properties, it does misrepresent fire because, as you may imagine, a fire pixel is a very complicated entity. There's a lot of different temperatures going on in that pixel. So these sizes and temperatures represent a hypothetical uniform fire whose properties produce the same radiant signature. This is potentially problematic. It means basically the size and the temperature really should not be taken literally. If you focus primarily on those, that's potentially a problem. It's also a problem because those are only produced for a subset of the fires. So you're missing fires if you're only looking at those products. Fire radiative power came about later in the last 15, 20 years as a way to measure fire intensity, use it in models. It's more directly related to the energy measured by the satellite. There's less math involved, less opportunity for error. It's also pretty close to the physical, the way we do it is pretty close to the physical definition of radiative power, which is on the right. The nice thing about power from modeling is that you can integrate it over time and get the fire radiative energy, which is proportional to the mass consumed. As I said, you can also do that with size and temperature, but due to the steps involved, you're adding error in that process. So go to the next slide. Obviously, a range of people use the fire products. Weather forecasters, NWS will use them, emergency managers, utilities have been making increasing use of these products. We have the hazard mapping system analysts and aerosol modelers also do. Next slide, please. Start getting to the fun stuff. So ABI can actually see fires in several bands. Now this 16 panel of all the ABI bands is perhaps a little confusing at first, but this is the camp fire from November of 2018. And I have dynamically scaled every panel to the data in that panel so that you can better see contrast. And if you watch, you can see that the fire signal shows up in most ABI bands, most of the long wave bands, and you can see it in several of the short wave bands. Frankly, depending on the circumstances, you might see it in any shortwave band except for probably blue. We've seen very intense fires even in the red band at night. Very weak signal, but it's there. So the radiance signature is actually across the spectrum, but it's strongest around 3.9 micron. So next slide, please. Looking at some real data in a little more sensible way. Now, granted, this is Brazil, maybe not directly related to most people's experience, but there's a lot going on in the scene, which is why I wanted to use it this time. This is just to locate you. We're just literally a randomly picked location in the center of Brazil when I made this case. There was nothing special about this day or that location. And on the next slide, I'll show you some of the raw satellite data. The fire temperature RGB that you might be familiar with, and fire radiative power, and the mask from the product that tells you about every pixel, which is actually already on this slide as well. So we go to the next slide and look at this animation. We'll let it loop for a few times while I talk about it. There are standard enhancements on the top panels, so things aren't flickering. And you can see the visible band and how smoke appears during the day, and the fires in the 3.9, and the pretty clear signal in the 11.2, but doesn't really show the fires. Bottom left is the fire temperature RGB. I'm using the standard formulation for that, which involves, if I remember correctly, I don't remember which bands exactly. I know it involves some shortwave bands. It also involves a temperature threshold, which is something I like to point out. Fires don't really, below a certain temperature, brightness temperature, won't show up very well in the RGB. You'll see them better in the raw imagery or if the algorithm actually catches them. That's something to pay attention to. And also is that during the day, the ground warms up, and that can look like fire signals too. So again, it's a very qualitative measure, which is part of the reason why we have quantitative products. Obviously it has its uses, but you can see that in the FRP panel and in the fire mask panel, it looks different than the RGB. And if you were to drill down into those specific pixels, you would see that some of them aren't actually on fire. They're just bare ground that are warming up during the day, but they look like they might be on fire in the RGB. So next slide. This is the ray of fire. This was on that first animation I showed you. And we're zooming in on it just to look at the various products, that, as well as the 3.9 micron. So we're showing all 4 products in 3.9 micron. Hopefully it's still animating on your end. It's not animating on mine. One of the points of this is to show that you have FRP for most of the fire pixels all the time. Size and temperature aren't always available, again, as I mentioned earlier. And so you're missing parts of the event when when you're looking at size and temperature, but not FRP. And below is just a plot of the sum of the FRP in the scene to show that diurnal signature and how things varied. Now you also see that during what is nighttime and certain times when the clouds pass over, fires that we can see don't show up in the product. Part of that is because their temperatures have dropped pretty low. Part of that is quirks about the product. Next slide. I'm going to talk about the Kincaid fire. The Kincaid fire has become kind of the poster child for both making no assumptions about when a satellite can see a fire and how quickly the algorithm can find something. So as you might be aware, on the 23rd of October, around 9:20 local time, the Kincaid fire started in Sonoma County. There was an alert wildfire camera near Santa Rosa that captured the start. You can see a light on the horizon, and then that light goes out, presumably when a power line fell, between 9:19:51 and 9:19:54, within that 3-second window that night. We believe that event started the fire. It intensified very rapidly. GOES 17 picked up the first hints of energy from that fire at 9:21. So within a minute and a half, presumably, of the start of the event, if that's when the event started. It might start a little bit earlier, and we just didn't see it yet, even in the camera. By 9:25, so within 5 minutes, the fire algorithm had picked it up. Now, notably, this is using the 1-minute mesoscale data produced at SBC, not NOAA's data. So there was a little bit longer lag in seeing it in the data that is available operationally currently. Let's just go to the next loop. I'll explain what the panels are when we're looking at it. So the background is that the event, and you can see that light went out and then the flickering fire appears. What you're seeing in the panels below are the 3.9 micron and the 11.2 micron, and those have stable fixed enhancements on them. In the middle is a radiant, what I call the 3.9 minus 11.2 radiance difference in 3.9 micron space. That's a way of looking at the energy difference between the two bands. And it's handy for drilling in on fires and has potential for being an avenue to really improve how we do fire detection. It also shows just how wide of a range the energy really changes over. At the start of the loop, you're talking about values of 0.03, 0.1. Toward the end of the loop, they're 5, 8, 25. So there's a couple orders of magnitude range in that radiance difference, which really highlights just how much signal that fire is putting out. You have the mask next to that and the FRP on the right. And as I said, this really is meant to highlight, since those panels are all correlated in time, by hand I might add, it shows really shows how well the satellite detected this particular event. Now, it was a very fast exploding event. While I don't have the canned examples handy, we are finding that this isn't entirely uncommon, even for events that don't blow up this quickly. We do find the signal, even if the algorithm doesn't find it, we're finding signal pretty early when fires are even as small as a couple acres in some cases. And I'm talking wildfires here. I'll show an example where even smaller fires have shown up shortly. So if we can go to the next slide. This is just highlighting that what I was talking about, and just showing the difference from 1 minute to the next of what the satellites saw. And yeah, it's a little noisy to look at, but the key point is 3 bands showed energy from that fire within 1 minute when that light went out. So next slide. I know there's a bunch of common questions I'll try to address real quick. So why do the satellites see different fires sometimes? There's a few different reasons for this. One is the satellites will see different aspects of the fire due to terrain. And that's the most common reason. You're on a hillside, one satellite has a better view than the other. The circumstances of viewing can also lead to things in the algorithm that change thresholds that are being applied, so that 2 measurements that look qualitatively the same may cause the algorithm to reach different conclusions. And that's an issue that needs more attention, but it does happen and may be responsible for some cases where you see different fires. How small of a fire can ABI see? Pretty darn small, it turns out. We are regularly finding house fires. In fact, these days, when I hear about any fire, especially in the Madison area, I'll go look at the raw data and see if I can find the signal, just to see how small these things we're finding. The algorithm is less sensitive by design, so that even though it has false alarms, it doesn't have even more of them. But it has managed to detect fires as small as an acre. Hot enough fires, like gas flares, can trigger the algorithm too. Known issues, there are plenty. There are false positives due to surface reflections from solar farms, other bright sources, thermal sources like refineries, and reflections off of water clouds are the most common reasons why the algorithm has trouble. As far as are there tips or guidelines for thresholds to apply, I would suggest that you focus, if you're in an operational scenario especially, focus on FRP. Size and temperature can be misleading, and they're very sensitive to instrument and remapping effects. They're there because they're legacy. They're not there because we sat down and thought, boy, this is what people really need and want and should look at. FRPs can range pretty low, but a threshold of about 75 megawatts will screen out a large number of false positives. That number could vary by region, of course. Just going to the next slide, I'm running out of time here. So this is an example from GOES 15 and GOES 16 of the 2 satellites seeing different fires, or seeing the same fire differently. If you look at this loop carefully, you'll see this. Some of the fires actually look remarkably similar despite the differences in the satellites. But the one dead center looks very different. It looks a lot hotter in 16 than in 15. Well, 15 was very far west at the time. And if you go to the next slide, 16 is on the east, 15 is on the west, and it turned out that the fire happened to be on an eastward facing slope. And that's why we ended up with such a disparity between the two. It makes intercomparing satellites hard, and not just the geostationaries, but with the polars as well. Between polar satellites, between polar and geo, terrain and other similar effects are always an issue. Next slide. As I mentioned, we see small house fires, and so there's 2 cases here. In one is the middle of winter, really cold night. A house fire showed up with about a 9 Kelvin difference above background that caused concern at the Weather Service office in Green Bay, and they were worried that maybe a plane had gone down. It turned out to be that house in the image in the lower left was on fire. And it's such a big temperature difference because it's so cold. In the middle of summer, that temperature difference would be much smaller. It would be similar to the half Kelvin on the right that came out of the Norman office, an example Todd Lindley provided with me, where they found a fire, a small house fire, just by visual interrogation. And one more slide here on solar panels. There's actually 2 of them, but we'll just look at one for time. I just wanted to show what solar panels can look like. As the sun marches across, the panels will brighten up, but they'll brighten up at different times. So the top is the visible band, 0.64, band 2. 3.9 is the next one, 11.2 is below, and then the fire product mask is on the bottom. And you can see, thanks in part to that contrast enhancement, the fires, or the solar panel, the solar fields lighting up the instrument. But one thing to note is that as you watch it, as the sun moves west, Those first couple fires over what is in Nevada, the one further west gets hotter first, and then the one to the east, and then they march west. And that's because Ivanpah, the solar farm there, is a big ring of mirrors focusing on a tower instead of a field of panels. And so that makes the solar farm issue interesting. And makes it hard to predict. And so we're working on that issue. We can just go to the next slide real quick. More solar farms. This is from Minnesota. So it's not just a Southwest thing. This happened a month ago, not even a month ago in Minnesota, just south of Minneapolis. There's like 9 or 10 different solar farms that pop up in this small area on that particular day. And it's a challenge to separate them from the background. And right now, the algorithm doesn't directly address that, but we plan to. On the next slide, we have future plans. There's a persistent anomaly mask, which is meant to deal with those solar farms, as well as other things like refineries and locations with common false positives that we'll be integrating. Also looking to eliminate reflections off of water clouds. Those are a real pain. They cause, there's a few different circumstances where they cause false alarms. And so if you see random sporadic false alarms on a day with small clouds everywhere, that's why. It's just the water cloud reflecting the 3.9 micron radiation. A couple other things that are also going to be dealt with that you may or may not have seen any evidence of, but they're definitely issues. And I ran over my time, but that's what I've got. I'm glad to answer questions.
Okay, thank you so much, Chris. I think we have actually a few questions here in the chat. And I'll just say before we go to the questions that we have certainly heard from the field about the need, I guess, from STUs to make sure that if you're looking for fires, that your forecasters know where all of the solar farms are in your forecast area. So that's as more solar farms are going in, they are causing these false detections at times, and they look very much like a fire in the imagery. Okay, so first question, and Chris, I'll let you take a stab at this first, and then maybe someone else from the field might want to pipe in and help. I think this is from Pat Spoden in Paducah, Kentucky. If he wanted to create a 4-panel satellite in AWIPS, what would the recommended images be? So essentially, if you had four panels with imagery related to fire detection, what would they be?
I would at least have 3. That 0.64, the 3.9, and the FRP. And the reason is, as much as I'm the keeper of the algorithm, I recognize that we're not beating the human eye, and we're a long way from doing that. And so visual interrogation is always important. The reason I would say FRP be in there is because it gives you a more quantitative measure of intensity. And once you've gotten used to the scaling, as with any imagery, it becomes easier to see the difference between different kind of tiers of fire. And the FRP does show you most of the detected fires. There's a small subset of possible fires that don't show up in FRP, but don't worry about those, because frankly, they shouldn't be there. It looks like they are pretty much always false alarms, and they'll be disappearing in a future update anyway. As a fourth panel, the short waves are not, bands 5 and 6 in particular can be helpful too. But with band 2 giving you smoke, or maybe looking at true color, some sort of true color is another panel to find smoke. Might not be a bad idea.
Anybody from the field want to weigh in? Matt Foster, I know you've done some fire experiments there at the OPG. Anybody else want to weigh in on a best practice for a 4-panel for fires? Just go ahead and unmute.
Hey Chris, this is Todd Lindley and Norman. Did you mention the nighttime fog difference channel, the 11 minus 3.9?
Well, I guess I forgot that you even had that available to you. Sorry, but yeah, that's a good one too.
Yeah, that's a really good one, Pat, because when you difference those, of course the differences are amplified, so fire pixels start to magnified and show up a lot better, usually earlier, not always depending on the intensity of the fire, but they can certainly show up earlier there.
Okay, any other comments on that? Hearing none, I just wanted to go to a comment, looks like from Ryan Walbrun there. Ryan, I don't know if you want to expand on this, but you were the IMET on the Kincaid fire. And you said that the ignition was a large metal tower where the transformer blew that caused the fire, that caused the light to go out on the alert fire movie. It wasn't a falling power pole. Anything you want to add to this scenario?
No, I don't know if you guys can hear me or not, but yeah, I mean, yeah, I'm not trying to pick on Chris's thing, but I've seen that a couple times now, and I feel like there's a narrative where it was a power pole that fell, and I just don't think that's true. It was, again, one of those large metal towers where the transformer blew, and that, I think that's the idea is that then threw off a bunch of sparks and got things moving. So just for information.
No, thank you very much. I appreciate that greatly. I mean, this is the kind of information I really want to hear about these kinds of events, so that we can establish when, if you've established when it really started, that helps me when I give this presentation. So I'll certainly update this going forward.
Some things can change that, and then all of a sudden,
Okay, thank you, Ryan. Question from Matt Foster. Do you know if anyone verifies the FDC products as accurately as possible on AWIPS? I think there have been issues in the past with the data quality flags being interpreted incorrectly.
Unfortunately, I don't know if anybody does it regularly. In the past, Scott Bachmeyer and Scott Lindstrom and I have looked at, and Tim Schmidt have looked at things in AWIPS and then found problems and bounced them off of Lee, Lee Byerly, back in the day. Right now, I'm not sure what's going on, if it's being looked at by anybody. There is a disconnect between the algorithm development side and the users. I can't even use AWIPS myself, for example, at least not directly right now. So I'm sure it's possible, but we just haven't gotten to that point where I do it. The answer is sometimes and sometimes not. But yeah, there definitely were problems. There were problems with the area showing up wrong. There were problems with the FRP being scaled wrong. There were a host of issues, and the mask has never been in AWIPS. So, just the binary detect, not detect, or with certain classes has never been there. And that's had an effect, because for a while, you really only had fire size and fire temperature and didn't even really have FRP functioning. And that led to a lot of people thinking that there was a problem with the product because they wouldn't see a fire for 2 hours. Well, we didn't have enough confidence, enough of a clear scene, whatever, to get the fire size and temperature. But the detections were there and the FRP was there, but you weren't seeing it in AWIPS.
Okay, I'm going to get one more question in here, realizing it's the bottom of the hour, so understand if people have to take off. But CCAS, have you examined detections at high latitudes? You mentioned viewing geometry issues.
There's been looked at it a bit. It is definitely challenging, and it hasn't gotten a ton of attention. Frankly, a lot of our attention has been focused on the CONUS viewing area, just because of the nature of the way all this product development has worked. I've looked at Canada and to a lesser extent Alaska, and seeing that it does remarkably well sometimes, but when the sun often produces problems during the day because of those shallow forward scattering cases in particular, and some other causes. But the pixel footprint is getting pretty large up there too, so our ability to detect fires is dropping off at those high latitudes, and that's another issue, which perhaps the next generation will help with.
Okay, thank you. I just wanted to add, looks like for Matt Foster here, he's mentioning there's an effort underway to make some AWIPs in a cloud instances available for developers to easily verify products in AWIP. So we are in the process of working with that, and that looks to be quite exciting.
That'll be great.
Yeah, so thank you so much, Chris, for your presentation today. I really appreciated it. A lot of good insight there. Wanted to remind everybody that next week we will not have a presentation in our normal Thursday spot, but we will resume the following week. Please be on the lookout from a email from the Tower S team with the topic for that talk. And if there's anything we can do for you, please feel free to contact the Tower S team related to AWIPS data flow or configuration of your satellite products in AWIPS. With that, we'll leave you and hope everybody has a good weekend whenever that comes for you. Take care now.